Today we'll talk about, now I will talk about the terrestrial and planetary geological mapping and overview. I will not go through the different geological maps that can be done on Earth or on planetary body, but I will just show you the basic principle of geological mapping on Earth and planetary bodies, so that all the people that will begin in this winter school will have an idea of the differences and similarities between different maps. So the geological processes on Earth can be just described thinking about a layer cake. So if we have a layer cake, we can form and we can start forming the layer cake at the beginning, okay, with layer on top of another layer. Eventually, we can want to cut it in pieces and overlap the pieces one to each other, so we can deform it. And finally, we can leave the cake there and wait some period of time until the cake can be disgregated and eroded and form deposits underneath it. So we have the shaping of the cake itself. And we can eventually take all these material that fall down from the cake and use it to form another cake again. So this is an ideal situation of what happens on Earth, in which we have a dominant water table, and underneath the water table we form normally sediments that become rocks. So we have the formation moment. Then at a given point we can eventually deform these sediments, and we have the deformation moment, and after that we can have the erosion, and on top of that we may have again the deposition and formation. So these three processes are the main ones that should be described in geological map. And actually, when we see any kind of panoramic view, we can see all these processes together. So for example, this is Cimon de la Pala and Dolomites panorama, and we see clearly layers. Okay, I don't know if you see my pointer or okay, but in any case,
we do.
Okay, we see layers. Sorry, we see layers, and from the bottom to the top. Sorry. Okay, that forms. And this indicates the formation process, the deposition process that has been recorded from the rocks. Then we may eventually see these layers, and if we follow them, some of them seem deformed. So it is the moment of deformation. So we can see the deformation process, and even the shape of the landscape is indicating the shaping moment. Okay, the erosion moment, and at the base of the cliff we see the deposits that it's still indicating the shaping process and the erosion. So these are the main processes that should be visible in any kind of geological map. We have seen that how to do polygons, polylines in QGIS before, and actually a map is an ensemble of different kind of vector layer. So we have polygons, and we have polylines, and we have points. And the formation process, the formation process is indicated by the geological units that are polygons of different color. And the different color indicate a different kind of age. And their description, the description of the geological units are in the legend there. The main geological unit that is described in a geological map is the lithostratigraphic unit. And the lithostratigraphic unit should have some important points, which are the same lithological character. The rocks should have the same lithological character. This means the same texture, grain size, composition inside the same units. So inside the lithostratigraphic unit. then there should be clear stratigraphic relationships. So it means that some units should be over the other, and this should be clear to see, and some other could cut the other, in case, for example, of igneous bodies, cutting and cross-cutting all the sedimentary ones, and some other could be one by side one to each other because they form more or less at the same time in different geological environment. I would say, I don't know, we can have a marine, deep marine environment, and at the same time we can have a shallow marine type close by, and they form in the same moment, but they have different lithological characters. So the last part, the geological unit, must be easily recognizable in the field. So these are the three main important bases for doing any kind of geological map on the Earth. Afterwards, we have the shaping process. So the shaping process is indicated in a geological map by polylines, and you see there blue polylines and of different kinds. Some of these polylines indicate faults, means planes in which across which we have the movement of a sequence of rocks with respect to another sequence, and then we have lines indicating faults. And because of the faults and the faults that can be seen with lines, we are able to recreate and reconstruct the geological sections, even considering the possible indication of points and the attitudes of the strata. That means the orientation of the strata with respect to the horizontal plane and the cardinal points. So with the orientation of the strata and these kind of lines that indicates the faults or the axial plane of the faults, we are able to reconstruct the subsurface geology. So we see here, for example, different kind of section, different kind of sequence that is repeated across faults and is folded by faults. And eventually, in this way, we can pass from a plan view of a geological map through a kind of 3D geological view in which we see the sequences, we see the faults, like this one or this one, and we see the faults. Finally, we have the shaping process. So what it is called the geomorphology. And the geomorphology could be so important that there can be maps dedicated only to geomorphology, in which we have the rocks that are not distinguishing on the basis of their stratigraphic relationship, so their relative age, which is younger and which is older, but they are just indicated as a different kind of lithotypes, so different kind of rocks. And all the other features are instead well depicted with polygons, with pale color, and patterns on top of which that indicates the process of erosion and deposition. That could be fluvial, could be glacial, could be gravitational. So the reddish one are gravitationally normally, and these are, I would say, kind of glacial deposits and so forth. And together with polygons, we have even symbols indicating the kind of process that we have. So most of these kind of features are distinguishable by the morphology, the topography they have, the roughness, the texture that they have. And they are indicated by forms like moraines or landslides or fluvial terraces and forms and loose materials. Eventually, we can add the geomorphological informations on top of the stratigraphic ones, like in this case, in which we have simplified the quaternary deposits, so the loose deposit related to the erosion, and simplified even the symbols of the geomorphology. And in this way, we have a complete geological map. If we focus a little bit on this map, we can see that there are areas that are darker with darker color here, and area with pale color that are surrounded by the loose materials and the morphologies. And this darker area indicate the outcropping material, so the rocks that can be recognizable, in which I can put my feet, or I can hammer. Okay, so these kind of rocks are the one that I would say are actually our data. All the other color are interpretation that are based on the data that are the rocks, and indicate eventually the one with stronger color indicates some subsurface material underneath 2 meters of loose material. So it's very likely that the rock is very close by. So another important point for doing a geological map is going to the field and find the outcropping material and distinguish it from all the surroundings. At the end, we can create the final geological map that is normally 4 or 5 times with a scale that it is 4 or 5 times smaller than the mapping scale. And in this map, we can see all the polygons for the formations, the lines for the deformations, the sections, the geological sections, and the legends. And from this kind of map, we can just look into the stratigraphy, we can infer the geologic evolution that in the case of the Dolomites that we have seen before can indicate, for example, the presence of atolls in the Permo-Triassic, and then possible volcanism in which we have contour part, which is outcropping on the Dolomites, and then we can have a coastal environment, and then we can have even deeper rocks up to very deep rocks. So we have different kind of environments that follow one over each other during time, and we can call and recall and tell a story about a geological drama about a given territory. And on top of this evolution, we may have the deformation. So again, the formation and then the deformations. And at the end of the formation of the Alps, in this case, we had the erosion, the formation of glacier, and the shaping, so the last process. So these 3 main processes actually are seeing everything of a given territory. So in summary, an Earth geological map is made by polygons, lines, and points, and the polygons are indicating the formational process and the geology, and the main unit is a lithostratigraphic unit or chronostratigraphic if we relate the lithostratigraphy, the relative age, with absolute ages. Okay, if we give real ages to the different kind of unit that we have. Then we have the lines and the points that indicate as the deformation processes. So the geological structures and the strata attitudes, the orientation of the strata with respect to the cardinal points and the horizontal plane. And then we have line and polygons that indicate the geomorphology and the loose deposit, and all together enable us to have the idea of the stratigraphic column that gives us a clear idea of the geological evolution during the formation process, and we can even infer the subsurface geology that is strongly dominated even by the deformational processes. So from a geological map, we can understand the geological evolution of the territory and the subsurface geology. So the main point here is, does it hold for planetary surfaces? Can we apply the same concept for planetary geological maps? So the main problem, one of the main problems on planetary surfaces with respect to the Earth are impact craters. We have impact craters also on the Earth, but they are not so frequent as on other planetary surfaces where we have no or very weak atmosphere. So we can have different kind of crater of different kind of sizes, very small up to very big. The most important classes of crater are the simple one with bowl-shaped and clear rims like Linné that we see there from the moon, and they are called simple one. And then we have the complex craters with central peak and very articulated and terraced walls that we see here that are bigger. This is the case, for example, from Tycho crater on the moon of 85 kilometers. But both of them form by impact with impactors, and both of them form in few minutes, seconds in some cases. So in I would say in some hundred of seconds. So we have in couple minutes or 3 minutes, we have the formation of a shape and deposit and deformations. So we cannot anymore think about a kind of sequence in which we have the formation, then the deformation, then the erosion and shaping, because everything is happening at the same time. So we have the deformation and the shaping in the 2 minutes, and in the same moment we have the formations of deposits that has been ejected and fallen down all around the crater itself. So the map of a crater actually is indicating the deposits, the loose deposits all around the crater itself, the morphology with some lines and the rock fall and the landslides inside the crater itself, or the pits or the peaks. That is a kind of deformations, all in the same 2 minutes. So in this case, the geological map is mainly a distinction of different kind of units on the basis of their geomorphology, and not really their lithostratigraphy, because they form exactly in the same moment. Another point which is quite different from a geological map on the Earth and the geological map on planetary bodies is that on the Earth, as we have seen, we find the outcrops that are the key for understanding the contacts between geological units. And we can go into the field and check them, but it's quite rare to go to the field on planetary body. We have to make photo interpretation. So actually, we clearly indicate the boundary between geological units directly from photo interpretation without going through the check and the rigorous points of observation in the field, in the case of planetary body. So we have the classical outcrop maps that are the base of a synthetic geological map. Actually, even on planetary surface, we map everything at higher resolution and at higher scale with respect to the final map, again, of 4 or 5 times with 4 or 5 times lower than the mapping moment, but still, even during the mapping, we have a kind of synthesis of the geological map, kind of interpretation of the contents between the units, much more free than in the case of the Earth. And actually, another point is that because we are photo-interpreting, we cannot use the concept of lithostratigraphic and chronostratigraphic units, in which we define very clearly the lithology, very clearly the stratigraphic relationship, and most importantly, we can distinguish them directly in the field. We can use only photo interpretation units that are morphostratigraphic units, and they are quite good. We can do a lot even with the morphostratigraphic units, but in this case, the morphostratigraphic unit is defined by its morphology. So the texture, the reflection, the albedo, the roughness of the surface, and eventually, if we are able, the stratigraphic relationship between different kind of morphologic units, okay? Different kind of photo interpreted units, because in some cases it's possible indeed to understand the stratigraphic relationship, but it is not a lithostratigraphic unit. So the relationship, it's not straightforward, cannot be straightforward like yes. So the final product actually show different kind of geological units that can be distinguished one to each other in function of the crater density. So that, for example, younger units have lower crater density with respect to older units. This is a way for understanding their stratigraphic relationship. Some cases we can see even overlapping relationship that help us. And then we have many, many kind of craters that indicates, and their deposits can be mapped one on top of each other. We can eventually see the overlapping relationship within them, but most importantly, we can even understand the stratigraphic relationship on the basis of the degradation of one crater with respect to the other. The older ones are more degraded than the younger ones. But at the end, the geological map from planets, it is a kind of morphostratigraphic map, which is in between the geomorphological map and the geological map. In between because we distinguish from texture and morphology the different units, so it's similar to the geomorphological map, but in the same time, we give an interpretation of the stratigraphy, so it's similar to the geological map. So it's not strictly a geological map, it's actually what we call a morphostratigraphic map. And for these reasons, it's even difficult to understand the subsurface geology because it's quite rare to have the strata attitudes and the attitudes of the fault of a given map, so that the cross-section in this case, if you see, are more simple with mostly horizontal line, and most of them are interpreted. You see dashed lines. All these are actually unknown contacts underneath the surface. So it means we have a lower reliability of our interpretation of the subsurface. And actually, one of the most important work of any geologist is not only to understand the geology of the surface, but from the geology of the surface, infer what it is underneath the surface itself. So in summary, for planetary morphostratigraphic maps, we have polygons that indicates the formation, if you want, process that are the morphostratigraphic units. Then we have lines and points. Lines are deformations, so we have faults and we have folds on planets, and they are indicating the same way than the case of the Earth. And then we have lines indicating just the geomorphology, but not the deposit, because the deposits are part of the morphostratigraphy. And all of them can give us an idea of the geological evolution, but a little bit more uncertain with respect to the Earth geological map, and a limited knowledge of the subsurface geology. So the major aim for us, for planetary geology, is to get closer to a real Earth geological map. And actually, there are attempts in the last decades, and we see, for example, Tsikowski, you have already seen this map, it's part of your exercise, and to the left, we see a classical geomorphological map, a little bit morphostratigraphic map, and to the right, there are a more detailed map in which some attempts have been done to relate the reflectance, which is, and the spectral properties of the terrain to the different units. So we can give, not the lithology if you want, but we can give some information about the spectra and relate them to the morphostratigraphic units. And here it's even more sophisticated attempt to get closer to Earth geology. We started from a morphostratigraphic map to the left. We have considered different kind of spectral indexes that are strictly related to the composition. And the main morphostratigraphic unit has been subdivided by themselves in subunits, indicating a different kind of spectral indexes. So the legends becomes more complex, if you want, but even more complete are the correlation map unit and the stratigraphy. So we are getting closer to Earth geological map. Another attempt is to go inside a crater, for example, and in a planet where liquid water was there, and study the sedimentary sequence that can be seen inside the crater, and that has not so didn't underwent on much was not involved so much on impact cratering. So we can see the sedimentary sequence that forms underneath water, similarly to what we do on the Earth, and work more on the stratigraphy, on the detailed stratigraphy, as in this case, in which in Eberswalde crater, it was possible to see different kind of stratigraphic sequence and different kinds of delta, and that has been mapped with the same criterion that we do on the Earth. Another way for getting closer to the geological maps of the Earth is to try to map in a way in which it is possible to understand very well the geometrical relationship of the units, even the subsurface, measuring thicknesses, for example, to the left, and or measuring strata altitudes to the right. And in this way, it's possible actually to have an idea of the subsurface geology like on the Earth. And finally, another approach is to go in detail and indicate the kind of map which is very, very close to what we do in the field, looking at very high resolution data, in which we can distinguish different outcrop and different units in very detail, as we have done or we normally do on the Earth, and as we have been done by ICPA in 2019 and 2020, looking at Apollo landing sites. So, in conclusion, I would say that any geological map should provide information on the evolution of a given territory in terms of formation, deformation, and shaping. This is quite more easy if you have no impact cratering processes, and much more difficult if you have them. The other geological maps are produced mainly through in situ surveys and based on lithostratigraphy, so lithostratigraphic units, and they are clearly distinguished one to each other on the basis of the lithology, and they should be visible in the field. The planetary geological map, instead, are produced through photointerpretation and are based on morphostratigraphy, which means that the morphology is the dominant factor that allow you to distinguish one geological unit with respect to another, plus the stratigraphy that can be inferred by the crater density, the possible overlapping relationship between the different units, and eventually the degradation if we are considering the craters. For several reasons, dominant impact cratering and lack of in situ information will be a long way, actually, for planetary geological map to approach the Earth geological maps. But actually, in the last decades, there are important research going on and important improvements that go in this direction. So including compositional or reflectance information within the geological map, including straightforward stratigraphic correlationship and stratigraphic analysis of sedimentary sequences, for example, on Mars, and some studies that aims on reconstructing the subsurface geology of planetary surfaces using different kind of geomodeling software, and finally the detailed mapping, which is one of the most important advanced focus of this winter school that aim at characterize the landing sites.